The fundamental theorem of calculus is a major theorem of calculus. And we're going to devote the next several videos concentrating on that specific idea. Now, again, in terms of learning objectives, what we want to get out of these videos is we want to be able to evaluate a definite integral using the fundamental theorem of calculus. Right now, the only way to evaluate a definite integral is through a Riemann sum. You're taking a limit, that sort of a thing. That's not a really good idea. Sometimes it's just almost impossible to do. Now, I want to understand the inverse relationship between a derivative and an integral. This whole idea of a derivative and an integral are very tightly intertwined with each other. And I want to understand the difference between and be able to calculate net and total area. We've already talked about the idea of net area and the idea of total area. And we want to use the fundamental theorem of calculus to allow us to actually calculate that area in a somewhat simplistic manner as compared to what we're doing now. Now, as I said a few moments ago, calculating the area under a curve using limits of Riemann sums is often either not possible to do because of the function, or it's incredibly complicated and labor intensive, so that actually makes it not practical. So fortunately, we do have this incredibly powerful result of calculus, which gives us a practical means of calculating the area under the curve. This result is known as the fundamental theorem of calculus. Now, as I said a moment ago, there's a very strong connection between differential calculus, the tangent line problem, taking a derivative, and integral calculus, which is based on the area problem. That connection is actually brought out in the fundamental theorem of calculus. When we review what the certain parts of this theorem actually tell us, we'll see what that connection actually is. Now, the fundamental theorem of calculus itself, before we actually hit the theorem, there's a couple things you need to understand. The fundamental theorem of calculus comes to us in two different parts. There's actually two parts to this theorem. Now, some textbooks refer to these as part 1 and part 2. Others refer to it as the first and second fundamental theorem of calculus. I want you to be aware of this because depending on which textbooks you happen to pick up and be looking at, you could see it written in these two forms. Now, you always need to be aware of these differences is simply in terminology and possibly in the order only. That's the only difference between these. What some textbooks simply call part 1, others might call part 2, and the other way around. Depends on how these books develop the ideas. Now, one order may seem more logical to the author than another. And what I'm about to present to you is the part 1 and then part 2 may or may not be part 1 and part 2 in any particular textbook. They could be turned around. So keeping that in mind, I'm going to present to you what I'm calling part 1 of the fundamental theorem of calculus. Now let's start with some curve, a to b, and I'm looking to evaluate this. I'm looking for the area. I'm looking to evaluate this. Now, the fundamental theorem of calculus says that if a function f is continuous on the closed interval a to b, and capital F is an antiderivative of f on a to b, then the integral from a to b of f of x dx equals f of b minus f of a. Now, let's break this down piece by piece for just a moment. F represents the antiderivative. So in other words, if you saw this as an indefinite integral and you found the antiderivative, you'd say that that is equal to f of x. That's one notation for the antiderivative. If we're dealing with specifically an area function, then we may call it a of x. Either way, both of these are the antiderivative of f. Now, what this theorem is saying is to evaluate this integral based on these antiderivatives. What we can do is simply say, hey, if I know these upper bounds a and b, this is equal to f of b, the antiderivative evaluated at b, minus f of a, the antiderivative evaluated at a. So a of x would be a of b minus a of a, using this notation where I go from a to b. And f and both a are actually the antiderivatives. So this integral from a to b of f of x dx, if I'm talking about the area function now, if I'm talking about area, is what we think of as a of x. But this a of x is going to actually be a of b minus a of a. So this is now not x, it's actually the area for specific values of a and b. So with this basic idea in mind, let's evaluate a couple real quick and see what we get. Let's evaluate from 1 to 3 of x squared plus 1 dx. The first thing I'm going to do is find the antiderivative. The antiderivative will be x cubed over 3 plus x. That's exactly what you would do if you solve this without the lower and upper bounds. This is simply the antiderivative. But now I'm going to evaluate from 1 to 3, and the common notation is a vertical bar with 1 and 3. Lower bound and upper bound. So now I'm going to evaluate this. This is going to be f of 3, this antiderivative at 3, which would be 3 cubed over 3 plus 3. That is f of 3, the antiderivative at 3, minus this thing at 1, which would be 1 cubed over 3 plus 1. Now this is just a number. And when you evaluate this, you'll get, see, 9 plus 3 minus 1/3 minus 1. And when you fiddle with that, you're going to get 32 over 3. Now, very quickly, let's do another quick example. Earlier, we took a look at a Riemann sum to estimate the area under the curve of x squared from 0 to 4. And we use a Riemann sum of n equals 20 to do an approximation. We looked at the left endpoint, the right endpoint, and then the midpoint. Now, using this technique, what I'm going to get is x cubed over 3 evaluated from 0 to 4. This is the antiderivative, which is going to be 4 cubed over 3 minus 0, which is 64 over 3. Or if I want to approximate that, that would be approximately 21.333, and the 3 repeats. Now, as a reminder, when we did the left endpoint, we ended up with an approximation of 19.76. We did the right endpoint, and that gave us an approximation of 22.96. And then we did the midpoint, and the midpoint approximation using Riemann sums gave me 21.32. In this case, 21.32 was extremely close to the actual. Now, this is the exact area under the curve. That's the exact amount of area that is truly under that curve. And then, of course, this is a decimal approximation for that value. Okay, moving on to this next example here, I need to integrate 0 to pi over 4 of secant squared x dx. Well, I'm going to do like I would have done with the indefinite integral, and I'm going to find the antiderivative. That's just tangent of x. And then I'm going to evaluate this from 0 to pi over 4. So that's tangent of pi over 4 minus tangent of 0. Well, tangent of pi over 4 is 1. Tangent of 0 is 0. So the area under the curve of secant squared between 0 and pi over 4 is just equal to 1. Now, something that you may have noticed is that if I would have done the indefinite integral of f of x dx, that would give me the antiderivative plus c. But nowhere in here did you see a c in here. Well, the reason for that is if I do this from a to b, f of x dx, what I get is this evaluated at b minus this evaluated at a. So I have f of b plus c minus f of a plus c, which equals f of b plus c minus f of a minus c, when I drop these parentheses, the c's cancel out, and that's just f of b minus f of a. That's what the fundamental theorem of calculus gives us. You do not need this constant of integration when you have a definite integral. It's only important when you have an indefinite integral. When you have a definite integral, the value of c is irrelevant because it will cancel out every time.